Somewhere in the deep sky, there are objects smaller than our galaxy that produce more energy than 1 trillion suns combined. For years, they showed up in telescope images as tiny, faint red smudges. Nobody knew what they were. Some ignored them. Some filed them away. Then James Webb looked. What it found rewrote the timeline of the universe, revealed black holes that should be impossible, and raised a question nobody has answered yet. We will visit the cosmic dawn, the objects that broke the standard model, and the discovery that changed everything we thought we knew about how the universe builds itself. If you enjoy the ride, subscribe and leave a like. Eyes open. Astronomers almost threw them away. In the early 2000s, deep sky surveys were pulling in thousands of images every night. Telescopes were scanning wide patches of sky, cataloging galaxies, stars, and the occasional smear of light that did not fit neatly into any category. And scattered throughout those images, easy to miss, were tiny reddish points. Faint, small, unremarkable at first glance. Most researchers logged them and moved on. A few flagged them as background contamination, the kind of optical noise that shows up when instruments stare too long into deep space. Some assumed they were distant, dust-choked galaxies seen edge on, the kind that look red because dust absorbs blue light and lets red light through. A reasonable guess. A wrong one. Nobody had the tools to look closer, and so the red dots sat in archives unexamined for years. This is where the story actually begins, because the fact that they were ignored tells us something important. Our understanding of the early universe was so confident, so settled, that astronomers were not really looking for surprises. The standard model of cosmology had been refined over decades. Scientists knew roughly how galaxies formed, how black holes grew, how long everything took. The timeline felt solid. The red dots did not fit that timeline, but nobody knew that yet. What made them red was the first clue, and it came down to a phenomenon called redshift. When an object moves away from us, the light it emits gets stretched. The faster it moves away, the more the light stretches toward the red end of the spectrum. In an expanding universe, objects far enough away appear red simply because the universe itself has been stretching their light for billions of years during its journey to us. A deeply red object, then, means a deeply distant object. An object so far away that its light left before most of the universe's current structure even existed. Picture sending a letter from across the country, but the mail takes 13 billion years to arrive. By the time it lands in your mailbox, the world that sent it is long gone. That is what these red dots were. Letters from a universe we had never seen. But faint letters are easy to ignore, and Hubble, the most celebrated space telescope of its generation, simply could not read them clearly enough to cause alarm. Its instruments were powerful, but they were built for a different kind of vision. Hubble saw best in visible and ultraviolet light. The red dots existed at wavelengths Hubble could barely register. So the mystery sat, patient, waiting. What changed was ambition. In the late 2000s and early 2010s, a new generation of astronomers started deliberately hunting for the faintest, most distant objects ever recorded. They were not chasing red dots specifically. They were chasing cosmic dawn, the period right after the Big Bang when the first stars and galaxies flickered on for the very first time. To reach that era, you need to see objects as they existed over 13 billion years ago. You need a telescope sensitive enough to catch light that has been traveling across an expanding universe for almost the entire age of everything. Hubble could not do it alone. James Webb was designed to do exactly that. And when the engineers and scientists running that telescope finally pointed it at some of those archived red smudges, the data that came back stopped people mid-sentence in conference rooms. The dots were dense, blindingly bright, and packed with something at their centers that had no right to exist that early in cosmic history. What they found inside was about to challenge a model that took decades to build. Hubble changed everything we knew about the universe. That part is real. It measured the expansion rate of space. It captured the deepest images ever taken of the sky. It gave us proof that supermassive black holes live at the centers of most large galaxies. For over 3 decades, it was the sharpest eye humanity had ever pointed at the cosmos. And it delivered discovery after discovery that textbooks had to be rewritten around. So it feels strange to say that Hubble had a blind spot, a literal one. The problem was wavelength. Light comes in many forms, and human eyes only detect a thin slice of it. Hubble was built to see roughly what we see, extended slightly into ultraviolet. That range was perfect for nearby galaxies, stellar nurseries, and objects within a few billion light years. Gorgeous, groundbreaking work. But the universe is about 93 billion light years across in the region we can observe. The objects from the very earliest era, the ones born within the first few 100 million years after the Big Bang, have had their light stretched so severely by cosmic expansion that it no longer arrives in visible wavelengths at all. It arrives in infrared, the same kind of invisible heat your body radiates right now. Hubble could detect some infrared, a narrow band of it, using instruments added during later servicing missions. And using those instruments, astronomers did manage to find some very distant objects. They found galaxies existing earlier than anyone expected. They pushed the frontier back, year by year, observation by observation. But the red dots, the truly compact, blindingly energetic objects sitting at the edge of observable time, Hubble caught glimpses of them and could not make sense of what it was seeing. The resolution was not sharp enough. The wavelength coverage was not deep enough. The objects appeared as smears, as noise, as ambiguous points that could have been almost anything. Think of it like trying to read a newspaper through a foggy window at night. You can tell there is text. You might even make out a letter or two, but the full sentence stays hidden. That was Hubble's situation with these objects. There was also a human factor. Science runs on consensus, and consensus in the early 2000s said that truly massive structures could not exist in the very early universe. The standard model predicted that galaxies and black holes needed time to grow. They started small and built up slowly through mergers and accretion, pulling in surrounding matter over billions of years. Under that model, a supermassive black hole in the very young universe was theoretically uncomfortable. A dense, blazing, compact object from that era, containing what looked like the mass of hundreds of millions of suns. That was not just uncomfortable, that was nearly forbidden. So even when data hinted at something strange in those early observations, there was a built-in tendency to find alternative explanations. Instrument error, contamination from nearby sources. The forbidden interpretation stayed off the table because the model said it should not be there. Science is supposed to follow evidence, but humans run science, and humans, even brilliant ones, carry assumptions into the lab. James Webb was designed without those assumptions baked in. Its mirror stretches almost 21 feet across. Its instruments detect infrared light across a range so wide and so sensitive that it can catch photons that have been traveling for over 13 billion years and still tell you exactly where they came from and how energetic their source was. When it turned toward the sky for the first time, it did not just see farther than Hubble. It saw differently. And what it saw made a very old assumption start to crack. The crack was about to become a fracture. The James Webb Space Telescope launched on Christmas Day, 2021. That detail matters. Decades of planning, billions of dollars, and a launch date that landed on a holiday. Engineers and scientists around the world sat at home with family and watched a rocket climb into the sky carrying the most complex observatory ever built. If anything went wrong during deployment, there was no repair mission possible. Webb orbits nearly 1 million miles from Earth, far beyond any crewed spacecraft's reach. Everything had to work perfectly, and for 6 tense months, as Webb traveled to its orbit and slowly unfolded itself, the world waited. Then, in mid-2022, the first images arrived. They were stunning in the way that made people cry in press conferences. Galaxies in breathtaking detail, stellar nurseries glowing in infrared, colors and structures invisible to every previous instrument, suddenly sharp and real. But the science teams were after something more specific than beauty. They pointed Webb at carefully selected patches of deep sky, regions where Hubble's older surveys had flagged unusual or unclassified objects. They ran long exposures, collecting light for hours, letting the telescope build up a signal from sources so faint they barely registered. And in those deep field images, the red dots appeared again. Dozens of them, sharper now, with enough detail to actually measure. Scientists extracted their spectra, the breakdown of exactly which wavelengths of light each object was emitting, which acts like a fingerprint. A spectrum tells you what something is made of, how hot it is, how fast it is moving, and critically, how far away it is. The distance readings came back first, and the numbers were extreme. These objects existed when the universe was between 500 million and 1 billion years old. The universe today is about 13.8 billion years old. So Webb was seeing these things as they were in the universe's early infancy, a time so remote that most of the structures we see around us today did not exist yet. Then came the brightness data. These objects were pouring out energy at a rate that made no sense for their apparent size. Compact, dense, extraordinarily luminous. The kind of output associated with a quasar, an actively feeding supermassive black hole surrounded by a blazing disk of superheated material. One team member described the feeling in the room as the data processed, quiet, then a few questions, then a long silence. Because what the numbers implied should not have been physically possible at that point in cosmic history. The black holes at the centers of these objects were already massive, hundreds of millions of times the mass of our Sun. Some potentially approaching billions of solar masses. And they existed at a time when the universe had barely had a chance to form stars, let alone build structures of that scale. The standard growth model for black holes requires time. A black hole starts small, pulls in surrounding gas, grows, slows, grows again. Even the fastest theoretical growth rates, maxing out what physics allows, could not get a black hole from stellar size to hundreds of millions of solar masses in under 1 billion years. Something had broken the model, or the model had never been right. The teams named the objects formally, but informally, in papers and presentations and hallway conversations, scientists started calling them little red dots. The nickname was almost funny given what they contained. What lived inside these dots was anything but little. Take everything you know about a galaxy, the sweeping spiral arms, the hundreds of billions of stars, the vast clouds of gas and dust stretching across tens of thousands of light years, the slow, majestic rotation that takes hundreds of millions of years to complete. One turn. Now compress all of that energy into a region smaller than the distance between our Sun and its nearest neighboring star system. That is roughly the scale of what a little red dot appears to be. The term comes from how they look in Webb's deep field images, tiny, reddish, compact points of light. Visually, they are unimpressive. You would walk past them on a chart without a second glance, but the measurements hiding behind that faint red smear reveal something that strains comprehension. The confirmed little red dots are among the most luminous objects ever detected from the early universe. Some of them pour out energy equivalent to tens of trillions of times what our Sun produces every second. every second. That is the sustained output, not a burst, not an explosion, but a constant roar of radiation blazing outward from a region of space you could theoretically traverse in a few light years. For context, the Milky Way galaxy contains somewhere around 200 to 400 billion stars. Its total light output, every star combined, is a fraction of what some of these compact objects radiate. A single little red dot, sitting in the infant universe, outshines our entire galaxy by factors that feel absurd to type. So what produces that energy? The leading explanation, supported by the spectral data Webb collected, points to an actively feeding supermassive black hole at the center. When a black hole pulls in surrounding gas, that material does not fall straight in. It forms a spinning disk, and friction inside that disk heats the material to extreme temperatures. At those temperatures, the disk radiates intensely across the electromagnetic spectrum. The process converts a significant fraction of the infalling material directly into energy, making it one of the most efficient energy release mechanisms in the known universe. A feeding black hole can outshine its entire host galaxy. At high feeding rates, it outshines thousands of galaxies simultaneously. That is the engine suspected inside each little red dot. But here is where the strangeness compounds. When scientists tried to measure the host galaxies around these black holes, expecting to find enormous structures surrounding such powerful cores, something odd emerged. The galaxies appeared unusually small and compact. In some cases, the host structure around the central engine seemed almost absent or too faint to properly detect. It raised a question that nobody had a clean answer for. Did the black hole form first, before the galaxy finished building around it? Did the energy blasting outward from the feeding black hole actually prevent star formation in the surrounding material, stunting the galaxy's growth, while the black hole itself kept consuming? Some researchers proposed the opposite, that these objects are dense star-forming regions, so packed with young hot stars that the combined light mimics what a black hole would produce. Thousands of massive stars crammed into a tiny volume, each burning at extreme temperatures. Both possibilities are extraordinary. Both imply the early universe was doing something much more violent and much more efficient than the models predicted. The answer would require digging deeper into the data, and the deeper scientists dug, the more disturbing the picture became. A candle produces about 1/10 of a watt of light energy. Our sun produces about 383 septillion watts. Those numbers are already incomprehensible to hold next to each other. Now consider that some little red dots produce energy outputs estimated at roughly 10 trillion times the sun's luminosity. Hold that image. Our sun, the star that powers every living thing on Earth, reduced to a faint ember compared to what sits at the center of one of these compact objects. Energy on that scale comes with rules. Physics sets hard limits on how much radiation a given mass can produce before the outward pressure of that radiation pushes away the very material the black hole is trying to consume. This limit is called the Eddington limit, named after the physicist who calculated it over a century ago. Exceed it, and the object tears apart its own food supply and shuts down. Most quasars operate near this limit. Some briefly exceed it in bursts. The little red dots, according to several analyses of Webb's data, appear to be operating at or beyond this boundary for sustained periods. Some estimates place certain objects at several times the Eddington limit. A team studying these objects described it as watching a fire consume its own oxygen supply and somehow keep burning hotter. How does something produce more radiation than physics says it should be able to sustain? Several ideas have emerged. One is that the black holes are spinning extremely fast, and a rapidly spinning black hole can extract energy from its own rotation in addition to the infalling material, temporarily pushing output beyond the normal ceiling. Another possibility is that the surrounding gas in the early universe was so dense and so cold that it could replenish the accretion disk faster than the radiation could blow it away, keeping the feeding process running at extreme rates longer than modern black holes ever manage. A third possibility is more unsettling. Some physicists have suggested that the Eddington limit itself may behave differently under the conditions present in the very early universe, when the cosmic environment was denser, hotter, and structurally unlike anything that exists today. If the rules bend under those conditions, then these objects are not breaking physics. They are revealing a version of physics we have not fully written down yet. That third option keeps theorists awake, and the energy problem, troubling as it is, was almost a distraction from the deeper issue underneath it. Because before you can worry about how much energy these objects produce, you first have to explain how they got so massive so fast. The black holes driving all of this output were already enormous when the universe was barely a toddler, billions of years before they should have reached that size by any conventional growth process. The mass problem, that was the real crisis waiting underneath the brightness data. And the numbers, when scientists finally committed them to paper, were enough to make even the most cautious researchers step back and say, something foundational may be wrong. Every black hole we have ever studied closely has a history we can trace, at least in theory. A massive star burns through its fuel, collapses under its own gravity, and leaves behind a black hole typically between a few times and a few dozen times the mass of our Sun. That is a stellar mass black hole. Small, dense, powerful in its neighborhood, but modest on a cosmic scale. To grow beyond that, a black hole needs to eat. It pulls in gas from its surroundings, merges with other black holes, and accumulates mass over vast stretches of time. The supermassive black holes sitting at the centers of modern galaxies, including the one at the center of our own Milky Way, reached their sizes over billions of years of this slow accumulation. The one at the Milky Way center, called Sagittarius A star, holds a mass of about 4 million times our Sun. A respectable size. It took billions of years to build. Now point Webb at a little red dot existing when the universe was 600 million years old. The black hole at its center carries a mass of several hundred million, sometimes over 1 billion, times the mass of our Sun. That is at least 200 times the mass of our own galaxy's central black hole, packed into an object that formed and grew in a period roughly equal to the time it took complex life to first emerge on Earth. The math does not work under standard models. Even assuming a black hole starts at the maximum allowed stellar mass and feeds at the absolute theoretical maximum rate, continuously, without pause, from the very first moment stars existed, it cannot accumulate that much mass in the time available. Scientists ran the calculations multiple times, different teams, different assumptions, different methods. The answer kept coming back the same way. The observed masses exceed what standard growth processes can deliver. One researcher put it plainly at a conference in 2023. The black holes we are finding with Webb are too big, too early, and we do not have a clean explanation. Several possible exits from this problem have been proposed. One is that astronomers are misreading the mass estimates. Black hole masses in distant objects are notoriously difficult to measure precisely, and some researchers argue the real values could be lower than they appear. That would soften the conflict with standard models. Another possibility is that early black holes grew through multiple simultaneous mergers, a kind of rapid assembly process that does not happen in the modern universe, because the cosmic environment today is far more spread out. In the early universe, everything was closer together. Mergers happened faster and more violently. A third option is the most radical. Some physicists suggest these black holes were never small to begin with. They propose that in the early universe, under conditions of extreme density and heat, gas clouds could collapse directly into black holes without forming stars first. No stellar explosion, no slow accumulation, just a massive cloud of primordial gas falling into itself, all at once, producing a black hole already carrying thousands or millions of solar masses from birth. Direct collapse black holes. The theory was proposed years before Webb launched. The telescope's findings gave it new urgency. And if direct collapse is real, it does not just solve the mass problem. It rewrites the birth story of the universe's most extreme objects from the ground up. Every black hole in our current models earns its mass. It starts small and builds up through a process that takes time, fuel, and favorable conditions. The idea that a black hole could simply be born with the mass of millions of suns felt, for years, like a shortcut that nature would not allow. Then the early universe started showing signs that nature might not have cared what our models allowed. The direct collapse theory begins with a very specific set of conditions that existed in the early universe and almost nowhere in the universe today. In the first few 100 million years after the Big Bang, the cosmos was flooded with intense ultraviolet radiation from the first generation of hot, massive stars. That radiation did something critical. It destroyed hydrogen molecules before they could cool down. Cooling matters enormously in star and black hole formation. Normally, when a cloud of gas wants to collapse under gravity, it cools as it contracts, and that cooling allows it to fragment. Fragmentation means the cloud breaks into smaller pieces, each of which collapses separately and forms a star. That is how most stars, and eventually most stellar black holes, get made. Strip away the cooling mechanism by blasting the gas with radiation, and something different happens. The cloud cannot fragment. It holds together as a single enormous mass. Gravity pulls it inward with nothing to stop or redirect the process. The whole cloud collapses in one piece. Under those conditions, the math produces a black hole potentially carrying between 10,000 and 100,000 times the mass of our Sun at birth. Some theoretical models push that birth mass even higher under extreme conditions. And a black hole that starts that large in an early universe dense with surrounding gas to consume can reach hundreds of millions of solar masses within a few 100 million years. That timeline fits what Webb is seeing. The trouble with direct collapse is that it requires a very specific and somewhat rare environment. The collapsing cloud needs to be close enough to a source of ultraviolet radiation to suppress its cooling, but not so close that the radiation itself disrupts the collapse. It is a narrow window. Some theorists have argued this makes direct collapse a minority pathway, responsible for only a small fraction of early supermassive black holes. Others have argued that in the early universe, those window conditions were far more common than they are today, because early galaxies were smaller, closer together, and emitting radiation at much higher rates relative to their surroundings. Webb's observations have not yet confirmed a direct collapse event in progress. The objects it found are already formed, already feeding, already ancient by the time their light reaches us. Catching one in the act of forming would require finding a massive gas cloud in the exact moment of collapse, which is an extraordinarily brief event on cosmic timescales. But the fingerprints direct collapse leaves behind, specifically the lack of a surrounding stellar population in some little red dots, and the extreme mass to galaxy size ratio, are exactly what several research teams have pointed to as indirect evidence that the process happened. The universe may have built its heaviest objects instantly before it even finished building everything else around them. And if it did that with black holes, what did it do with galaxies? Imagine a construction site where the workers arrive on day 1 and by day 3 have finished a skyscraper that should have taken 5 years. That is roughly the situation astronomers found themselves staring at once. Webb started sending back data on star formation rates in the early universe. Stars form from gas. Cold gas clouds collapse, heat up at their cores, and ignite nuclear fusion. The rate at which a galaxy converts its available gas into new stars is called the star formation rate, and in modern galaxies like our Milky Way, it proceeds at a measured pace. The Milky Way produces somewhere around 1 to 3 new stars per year, efficient enough to maintain the galaxy calm enough that the whole process feels almost glacial. Early galaxies were operating at a different tempo entirely. Webb's observations of galaxies from the universe's first billion years revealed star formation rates reaching hundreds, in some cases over 1,000, new stars per year, packed into galaxies smaller than the Milky Way, running on gas supplies that, at those consumption rates, should have been exhausted in a cosmically brief period. These early galaxies were burning through their fuel at a pace that the standard model struggled to account for. The model predicted star formation in the early universe would be vigorous, yes, but spread out as galaxies gradually assembled their mass. What Webb found instead were galaxies that appeared to have already assembled enormous stellar populations. In what amounted to a cosmic sprint, some of these galaxies, detected in Webb's deep field images, contained stellar masses that, under the standard model, should have taken several billion years to accumulate. They existed at a point when the universe was only a few % of its current age. The star formation efficiency in these objects was far beyond what simulations predicted. Efficiency here means the fraction of available gas that actually gets converted into stars before feedback processes. Mainly energy from the stars and black holes themselves blow the remaining gas away. Modern galaxies convert a relatively small fraction. Some early galaxies appeared to be converting gas into stars at rates approaching the theoretical maximum. A few research teams proposed that the initial conditions set by the Big Bang itself might have produced denser gas filaments in certain regions, giving early galaxies a richer food supply than the average model assumed. Others pointed to differences in the early universe's chemistry. The very first stars contained no metals, no elements heavier than hydrogen and helium, and that chemical simplicity may have allowed gas clouds to collapse and form stars more easily than they do today. There is also a feedback loop worth understanding. Rapid star formation produces massive, short-lived stars that explode quickly as supernovae. Those explosions enrich the surrounding gas with heavier elements and heat the environment. But in the densest early galaxies, the gas supply may have been so abundant that even this feedback could not slow the process for long. The picture emerging from Webb's data showed an early universe that was chaotic, dense, and building structure at a pace that our models had systematically underestimated. And inside those rapidly building galaxies, surrounded by dense gas clouds and extreme stellar activity, the black holes at the center were also growing at speeds that matched the frantic environment around them. Everything was accelerating, and the reason why was buried in something the universe was still hiding. Some of the most energetic events in the universe have gone undetected for decades because of something as mundane as dust. Dust in space is different from the dust on your shelves. It consists of tiny particles, mostly carbon and silicate grains, smaller than the width of a human hair. On their own, they seem trivial, but pack enough of them around an energetic source, and they become a wall. Visible light and ultraviolet radiation cannot pass through dense dust clouds. They get absorbed and re-emitted as infrared, the same heat-based radiation that James Webb was specifically built to see. This created an extraordinary situation. Some of the most powerful objects in the early universe may have been completely invisible to every telescope humanity operated before Webb. Shrouded inside thick cocoons of dust, blasting out energy that transformed into infrared and went undetected for decades. When Webb looked at certain little red dots, it found exactly this. Objects whose extreme infrared brightness suggested a powerful energy source buried behind dense dust. The dust absorbed the raw radiation from the central black hole or star-forming regions, heated up, and re-radiated that energy at longer wavelengths that Webb could detect with precision. Peeling back those layers through spectral analysis, scientists found signatures suggesting these were actively feeding black holes, surrounded by gas and dust so thick that even Webb could not see the central engine directly. The black hole announced itself through the glow of the material it was cooking. One research team estimated that a significant fraction of all actively feeding black holes in the early universe may be dust obscured, meaning the census of early supermassive black holes astronomers had built up before Webb could be drastically incomplete. The objects they found represent the tip of something much larger. This raised an immediate and uncomfortable question. If dust was hiding entire populations of feeding black holes from all previous observations, how badly were the models built on those incomplete observations skewed? The short answer is substantially. Cosmological models are calibrated to match what we observe. If a large fraction of the most energetic objects in the early universe were invisible before Webb arrived, then the models were calibrated to a universe with far fewer such objects than actually existed. Simulations, predictions, growth timelines for black holes and galaxies, all of them may need adjustment to account for a hidden population that was there all along. There is also a stranger implication. Dust in the early universe had to come from somewhere. Heavy elements like carbon and silicon, the building blocks of dust, are forged inside stars and scattered by supernovae. In the very young universe, there had been only a small number of stellar generations, meaning the amount of dust available should have been limited. Finding dense dust clouds around some little red dots suggested that star formation and stellar death in those regions had already proceeded through enough cycles to produce significant dust even in the early universe. Another sign that the early cosmos was building and destroying things faster than the models predicted. The dust was not just an observational obstacle. It was evidence of a violent history that had been written and partially erased before most of the universe's current structures even began to form. And underneath that dust, something was still burning at a rate that the next data set would make even harder to explain. There is a moment in every story before the lights come on. For the universe, that moment is called the cosmic dark ages. After the Big Bang, the universe expanded and cooled for hundreds of millions of years. There were no stars, no galaxies, no light of any kind except the faint afterglow of the Big Bang itself, slowly cooling and stretching into invisibility. The cosmos was a vast, dark, lukewarm sea of hydrogen and helium gas, drifting and clumping under gravity. Then, the first stars ignited. Astronomers call the period when this happened cosmic dawn, roughly between 100 million and 500 million years after the Big Bang. The first stars blazed to life inside dense gas filaments, far more massive and far hotter than most stars born today. They burned fast and died violently, seeding their surroundings with heavier elements and unleashing floods of ultraviolet radiation that began stripping electrons from the surrounding hydrogen gas in a process called reionization. The universe went from dark and foggy to transparent and structured in a cosmically brief window. That transition shaped everything that followed, including the formation of every galaxy, every black hole, every planet, and eventually every living thing. Webb's deepest observations are reaching into the tail end of the cosmic dark ages and the beginning of cosmic dawn. The little red dots sit inside this window. They are relics of the first era of structure, objects that formed and evolved during a period that, until Webb launched, existed mostly in theory. The significance of seeing them directly cannot be overstated. Previous telescopes showed us what the universe looked like after cosmic dawn had passed. Webb is handing us actual data from while it was happening. And what that data shows is an era far more violent and far more productive than anyone modeled. The first structures were massive. The energy outputs were extreme. the building happened fast. This was the universe at full intensity, not the slow, orderly assembly that models predicted. Reionization itself, the process by which the early stars and galaxies stripped the fog away from the universe, is now thought to have been driven in part by objects like the little red dots. An actively feeding black hole surrounded by young hot stars produces a torrent of ionizing radiation. Multiply that across hundreds of such objects spread across the early universe, and you have a significant engine driving the transition from dark to light. This reframes the little red dots from interesting anomalies to central characters in the universe's origin story. They may have been responsible for clearing the cosmic fog that allowed the modern observable universe to form. Without objects like them blazing during cosmic dawn, the universe today might look structurally different in ways that are difficult to predict, but probably significant. The reionization window, when it opened, set the conditions for everything that came after, including the stars that eventually forged the elements in your body. But knowing they existed and knowing what they were doing are different problems. And the closer scientists looked at the Standard Model's predictions for this era, the more the data Webb was collecting pushed back. Something in the foundation was giving way. The Standard Model of cosmology is one of the most successful frameworks in the history of science. It describes how the universe began with a rapid expansion from an extraordinarily hot, dense state, how matter clumped together under gravity to form the first structures, how dark matter provided the gravitational scaffolding that galaxies grew along, how dark energy is currently accelerating the universe's expansion. Across decades and thousands of experiments, this model has matched observation after observation with remarkable precision. It is a framework built on hard evidence, and dismantling it is not something scientists do lightly. Before Webb launched, the model's predictions for the early universe had never been seriously tested by direct observation. The telescopes of previous generations simply could not see that far with the necessary detail. Webb could, and almost immediately, the data began applying pressure. The first and most widely discussed tension was the abundance of massive, bright galaxies in the very early universe. The Standard Model predicts that the early universe should contain mostly small, faint, disorganized proto-galaxies, the raw material that will eventually be assembled over billions of years into the large structured galaxies we see today. Webb found bright, massive galaxies existing earlier than they should. Multiple teams independently confirmed this across different deep field observations. These were galaxies containing stellar populations that, under standard assumptions, should have taken billions of years to build. They existed when the universe was only a few 100 million years old. One early analysis attracted significant media attention by suggesting that the total stellar mass locked up in some of these early galaxies was so high it exceeded the total amount of matter the Standard Model predicted should have been available for star formation at that epoch. That specific claim was later debated and refined, with some researchers arguing the mass estimates carried significant uncertainties. But even after adjusting for those uncertainties, the tension remained. Early galaxies were more massive, more numerous, and more structured than the Standard Model's simulations had produced. The little red dots added a different and sharper version of this tension. Their black holes were too massive for the time. Their luminosities suggested feeding rates that strained physical limits. Their host galaxies appeared compact and dense in ways that did not match the gradual assembly picture. Not every cosmologist viewed this as a crisis. Many pointed out that models are not broken by individual observations. Science advances through accumulation of evidence, and Webb had been operational for only a short time. Systematic uncertainties in distance measurements, mass estimates, and spectral interpretations could shift some of the numbers. A measured but honest statement from one senior cosmologist summarized the situation cleanly. We are finding things that our models said were unlikely or very rare, and we are finding them consistently, and that means something in the model is incomplete or wrong. Incomplete or wrong. The distinction matters enormously. A model that is incomplete can be extended and refined. A model that is wrong at its foundations needs replacement. The scientific community had not yet determined which category applied, but the evidence pressing on that question was growing every week. Webb sent data home, and the strangest piece of that evidence had not yet fully revealed itself. James Webb did not arrive quietly. Before its first official science images dropped in July 2022, astronomers had already been running early release observations, testing the instruments, and calibrating the systems. Even in those test phases, the data was producing results that circulated through the community with urgent energy. One early release observation pointed Webb at a tiny patch of sky that Hubble had previously imaged in its famous deep field surveys. Hubble's deep field images, built from hundreds of hours of exposure, showed thousands of distant galaxies as faint smears and colored blobs, the most profound long-exposure photographs ever taken. Webb's image of the same region arrived with a resolution and sensitivity that made Hubble's version look like a first draft. The same patch of sky now revealed thousands of additional galaxies that Hubble had missed entirely, many of them sitting at distances far beyond what Hubble could detect. Galaxies that had been invisible a year earlier were now sharp enough to measure spectroscopically. Distance measurements came back on dozens of objects simultaneously. Several of them set new records for the most distant confirmed galaxies ever observed, pushing the frontier back past 13 billion light-years with ease. But the record-breaking distances were almost secondary. The more significant issue was what those galaxies looked like at those distances. They were structured. Some were already spiral-shaped, showing the organized rotational pattern that takes billions of years to develop under standard models. They had color gradients suggesting populations of stars at different ages. They had defined central cores, galaxies from a time when the universe was only a few 100 million years old, showing structural complexity that the models said should come much later. One galaxy detected in early Webb observations existed when the universe was approximately 320 million years old. Its light has been traveling for over 13 billion years to reach us. And it was already a recognizable galaxy, containing stars, structure, and chemistry, at an epoch the standard model reserved for formless gas clouds and the earliest protostructures. As months passed and more data accumulated, the list of early, unexpected, structurally mature objects grew. Teams in different countries, using different analytical approaches, kept landing on the same uncomfortable conclusion. The early universe was building things faster than predicted. The timeline that textbooks had printed for a generation was not wrong in every detail. Cosmic dawn still happened. The Dark Ages still preceded it. The Big Bang still initiated everything. But the speed at which structure assembled, the mass of the first objects, the efficiency of the first star formation cycles, all of these were off in the same direction. The universe built up faster and earlier than the models said was reasonable. Revising those timelines would require adjusting the inputs that generated them, and adjusting those inputs had consequences that rippled through every subsequent era of cosmic history. The physics of the early universe touches the physics of everything that came after. What Webb was handing astronomers was extraordinary, an urgent, data-heavy invitation to reconsider something they had considered settled. And the reconsideration was about to produce one of the strangest sub-debates in modern astrophysics. Saying the Big Bang model might need revision is different from saying the Big Bang did not happen. That distinction matters, and it gets blurred badly in popular coverage. The Big Bang itself meaning the universe began in an extremely hot, dense state and has been expanding ever since, is supported by mountains of independent evidence. The cosmic microwave background radiation, the observed ratios of hydrogen and helium in the universe, the redshift of distant galaxies, all of it points coherently to a hot origin and an expanding cosmos. When scientists say Webb's findings create tension with the standard model, they mean the specific mathematical framework built on top of the Big Bang, the one that includes dark matter, dark energy, and precise predictions about when and how structure formed. That framework, called lambda cold dark matter, is the version under pressure. Lambda cold dark matter makes specific quantitative predictions. It predicts how many galaxies of a given mass should exist at a given distance. It predicts the typical sizes and structures of early galaxies. It predicts the growth rates of black holes at various epochs. These predictions come from simulations run over decades, refined repeatedly, and tested against every observation available. Webb's observations sit outside those predictions in a consistent and uncomfortable way. Several theorists have proposed modifications to address the tension. One modification involves the nature of dark matter itself. The standard model assumes dark matter consists of slow-moving, heavy particles that form large clumps and pull normal matter in around them gradually. Some researchers have proposed that dark matter behaves differently than assumed, interacting with itself or with normal matter in ways that could accelerate early structure formation. A faster clumping dark matter model would allow the gravitational seeds of galaxies to grow earlier and more efficiently, producing the massive structures Webb is finding without abandoning the broader framework. Another proposed modification targets the period just after the Big Bang called inflation, a phase of extremely rapid expansion that stretched quantum fluctuations into the density variations that seeded all future structure. The specifics of inflation, how long it lasted, exactly how it ended, what field drove it, remain uncertain. Some theorists have proposed inflation models that would produce a slightly different distribution of density fluctuations, generating more early massive structures than the standard version predicts. These are refinements, extensions of the existing model, rather than replacements for it. But a smaller number of researchers have raised a more radical possibility that the cosmological constant, the value representing dark energy driving the universe's accelerating expansion, may vary over time rather than being fixed. A changing dark energy value would alter the entire expansion history of the universe and could shift the timeline of structure formation significantly. No consensus exists on which of these modifications, if any, is correct. The field is in an active and genuinely open phase. Scientists are debating not just the data, but the theoretical language they need to interpret it. What Webb has done is force that debate to happen at a pace and with a specificity that was not possible before. The telescope is not just finding anomalies, it is producing a catalogue of precise, repeated measurements that demand precise theoretical answers. And the most precise, most repeated, most disturbing measurement of all was still sitting in the little red dot data, waiting for the next round of analysis. After 2 years of Webb observations, the scientific community reached a consensus on exactly one thing about the little red dots. The consensus was that there was no consensus. Several competing interpretations of what these objects fundamentally are remain active and unresolved. Each is backed by real data. Each has significant problems, and the debate between them cuts to the heart of how matter, energy, and gravity behave at the most extreme scales the universe produces. The leading interpretation is the active galactic nucleus model. Under this view, each little red dot is powered primarily by a supermassive black hole consuming surrounding material. At an extreme rate, the black hole sits at the center of a compact, dense host galaxy, and the energy output comes from the superheated accretion disk surrounding the black hole as it feeds. This model explains the extreme luminosities and fits the spectral signatures Webb detected in many of these objects. The problem with this interpretation is the mass requirement. Producing the observed luminosity through black hole accretion requires a black hole already enormous by the time of observation. And as discussed, getting a black hole that massive that early is theoretically very difficult under standard growth models. The active galactic nucleus interpretation solves the energy problem and creates a mass problem. The second major interpretation is the extreme starburst model. Under this view, the little red dots are densely packed regions of extreme star formation, with so many massive hot young stars crammed into a small volume that the combined light mimics a quasar-level energy output. Some early analyses of certain objects suggested the spectral signatures could be consistent with very hot stellar populations rather than an actively feeding black hole. The problem here is efficiency. To produce the observed luminosity through stars alone would require packing an almost unimaginable number of them into a tiny region. Some calculations suggest stellar densities far beyond anything observed in the most intense star-forming regions in the modern universe. The starburst model solves the mass problem and creates a density problem. A third interpretation proposes that both are happening simultaneously. An actively feeding black hole sitting inside an extreme starburst galaxy, with both processes contributing to the total energy output. This combined model is attractive in principle, but requires explaining how both extreme conditions coexist and sustain each other at the same location during the same narrow period. A fourth and more exotic proposal has attracted serious attention from a subset of theorists, that some little red dots may be a new class of object that does not fit cleanly into any existing category. Objects where the boundary between a black hole's accretion zone and the surrounding dense stellar population blurs in ways that produce physical conditions with no modern analogue. The Webb data alone cannot fully distinguish between these options in all cases. Different objects in the little red dot catalogue may belong to different categories. Some may be black hole dominated, some may be starburst dominated, some may be both. What they share is the scale of their impact on everything astronomers thought they knew about the early universe. The answer to what they really are may require a measurement that even Webb cannot make cleanly. Something much stranger was about to emerge from the debate. At the centers of the little red dots, in whatever form they take, gravity operates at intensities that have no equivalent in the modern universe. Gravity is the weakest of the four fundamental forces. It is weaker than electromagnetism, which is why a small magnet can lift a metal object against the gravitational pull of an entire planet. It is weaker than the nuclear forces that hold atomic nuclei together. On human scales, and even on stellar scales, gravity is a slow, patient force. It accumulates over time, and its effects are majestic but not instantaneous. Push enough mass into a small enough space, and patience runs out. At the densities present in an actively feeding supermassive black hole's environment, gravity stops being a background feature of the landscape and becomes the dominant condition of existence. Space itself curves sharply around the central mass. Time runs slower near that mass than it does farther away, a confirmed prediction of general relativity that has been measured directly near Earth and in pulsar systems. At extreme densities, this time dilation becomes severe. For materials spiraling toward a supermassive black hole in the little red dots, the final moments of infall occur in conditions where the physics we observe in daily life no longer applies in recognizable form. The infalling gas is compressed to densities comparable to those inside atomic nuclei. Temperatures reach trillions of degrees. Magnetic fields generated by the moving charged particles reach intensities strong enough to accelerate particles to near the speed of light and launch them as jets, stretching for thousands of light years. Those jets, observed in many quasars and active black hole systems, carry energy far outside the black hole's immediate environment. They punch through the host galaxy and inject energy into the surrounding gas. At the velocities and power levels present in the early universe, jets from a little red dot's central engine could heat and disperse enough gas to prevent star formation across an enormous volume surrounding the black hole. This mechanism, called black hole feedback, is one of the most important processes in all of galaxy evolution. The black hole regulates its own galaxy's growth by periodically blasting it with radiation and jets. Too much star formation triggers a feeding burst that produces feedback that slows the star formation, a self-regulating cycle. In the early universe, with everything denser and more compact, this feedback operated at full intensity and in close quarters. The black hole and the surrounding stellar material were locked in a violent back and forth from the very beginning. What general relativity predicts about objects at this extreme remains partially testable and partially theoretical. Webb can measure the outputs, but cannot see inside the event horizon, the boundary beyond which no information escapes. The physics at and beyond that boundary, the singularity at the black hole's core, remains genuinely unknown. Some physicists believe general relativity itself breaks down inside a black hole at extreme densities, requiring a theory of quantum gravity to describe correctly. That theory does not yet exist in complete form. So the little red dots sit at the intersection of what we can observe, what our best theory predicts, and what remains fundamentally unresolved in physics. And that intersection, it turned out, was about to get even more crowded. Every image Webb captures is a time machine image. Light travels fast, roughly 186,000 miles per second, fast enough to circle Earth 7 times in a single second, fast enough to reach the moon in about 1.25 seconds, fast enough to reach the sun in about 8 minutes. At those speeds, cosmic distances become cosmic time delays. The light from a star 100 light years away left that star 100 years ago. You are seeing it as it was, not as it is. For a star 400 light years away, you are seeing 400 years into its past. The star might not even exist anymore. Now extend that logic to the little red dots. The most distant confirmed little red dots sit at distances over 13 billion light years from Earth. The light captured by Webb from these objects left them over 13 billion years ago. The universe was less than 1 billion years old when that light began its journey. The objects themselves have had 13 billion years to evolve, possibly die, merge with other structures, or transform into something else entirely. We have no direct knowledge of what they became. We are seeing a frozen moment in an object's ancient past, preserved in light and delivered to a telescope in the present. This creates a profound measurement challenge. When astronomers calculate the mass, luminosity, or feeding rate of a little red dot, they are measuring properties from 13 billion years ago. The black hole at the center may have grown enormously since then, or it may have exhausted its fuel supply and gone quiet. The host galaxy may have merged with neighbors and become a massive elliptical galaxy, or it may have been disrupted and dispersed. There is no way to observe the same object across its full lifetime. Astronomers piece together evolutionary histories by looking at large populations of objects at different distances, which correspond to different epochs, and inferring the typical path from one stage to the next. This technique works when the populations at different epochs make sense as connected evolutionary stages. The tension created by Webb's findings is that the populations at the earliest epochs look so extreme that connecting them smoothly to what came later requires processes that the models have not fully accounted for. The light travel time also creates a visibility horizon. There is a distance beyond which the universe becomes opaque to any form of electromagnetic radiation. Before reionization was complete, the universe was filled with neutral hydrogen gas, that absorbed light. Webb can see through the reionized universe, but approaches the edge of the opaque era with its most distant observations. The little red dots sit near that edge. Some of them are so distant that their light barely squeezed through the end of the opacity window before it opened fully. They are some of the last objects visible before the universe, going backward in time, becomes a fog that even Webb cannot penetrate. Whatever exists beyond that fog, the first generation of objects born into the universe before reionization, has never been directly observed. It remains the last true frontier of observational astronomy. And there is strong reason to believe that whatever is hiding there will be even more extreme than what Webb has already found. They are gone. Search the modern universe for objects matching the description of the little red dots: compact, extraordinarily luminous, hosting black holes at extreme feeding rates inside dense early galaxies. And you find a very different landscape. The modern universe contains massive galaxies and supermassive black holes at their centers. But the intensity of what Webb found in the early universe has no direct counterpart today. The little red dots burned out. The question is how, and how fast. The most widely supported explanation involves fuel exhaustion. A black hole feeding at the extreme rates suggested by the little red dot data consumes its available gas supply rapidly. The intense radiation produced during peak feeding heats the surrounding gas and can drive it outward in powerful winds. Once the cold, dense gas that feeds the accretion disk is consumed or expelled, the feeding rate drops. The luminosity collapses. The compact, blazing object becomes a quieter, larger galaxy with a massive but dormant black hole at its center. This transition from extreme activity to quiet dormancy is observed in closer, more recent quasars as well. The process is called quenching. A galaxy goes from rapid star formation and active black hole feeding to a relatively passive state where old stars age and few new ones form. Quenched galaxies tend to be large, red ellipticals, the most common type of massive galaxy in the modern universe. Some researchers believe the little red dots are the extreme early ancestors of these modern quenched giants. The objects Webb found, blazing at full intensity in the young universe, eventually consumed their fuel, quieted their central black holes, and settled into the passive, old star-dominated structures we observe billions of years later. If this evolutionary path is correct, the supermassive black hole at the center of a typical massive elliptical galaxy today carries the memory of a violent early phase hidden in its mass. A billion solar mass black hole sitting quietly in a modern galaxy may have spent its early existence as the engine of a little red dot, consuming gas at hundreds of times the rate that produces its current, almost imperceptible activity. The Milky Way's own central black hole, Sagittarius A star, shows signs of past activity far beyond its current trickle feeding rate. Enormous lobes of energetic gas called Fermi bubbles extend above and below the galactic plane, likely produced by a period of much more intense black hole activity millions of years ago. Whether the Milky Way ever hosted a full quasar-level burst remains an open question, but the physical signs of a more active past are present. A second possibility for the disappearance of the little red dots involves mergers. As the universe aged, dense concentrations of early galaxies were drawn together by gravity and merged into larger structures. The compact, intense objects of the early universe were absorbed into larger galaxies, their identities erased through repeated mergers over billions of years. Under this scenario, the descendants of the little red dots are not recognizable as distinct objects because they have been blended into something much larger and more complex. A third and more unsettling possibility is that some little red dots were genuinely transient phenomena with no long-lived descendants. Objects that formed under early universe conditions so specific that they consumed everything available, collapsed, and left behind black holes embedded in dispersed remnants, too faint to identify as related to their origin. The universe cleaned up after itself, and what it replaced the little red dots with was the calmer, more structured cosmos we see today. But something crucial happened in between, and understanding that transition is where the deepest remaining mystery sits. A black hole feeds, and while it feeds, it destroys the very environment that made it possible. This sounds self-defeating, and in a sense it is. But the mechanism is real, confirmed in dozens of modern galaxies, and in the early universe it appears to have operated at a scale that reshaped entire regions of space. Understanding it changes how you see every large galaxy in the sky, including the one you live inside. When a supermassive black hole consumes gas at a high rate, the accretion disk surrounding it becomes one of the most energetic environments in the universe. The disk radiates intensely across the entire electromagnetic spectrum. Powerful magnetic fields threading through the disk launch two opposing jets of plasma outward along the black hole's rotation axis, moving at a significant fraction of the speed of light. And at the outer edges of the disk, radiation pressure drives winds of gas outward at millions of miles per hour. Those winds and jets carry energy deep into the host galaxy. They heat the surrounding gas. They compress some clouds and shred others. They push cold molecular gas, the raw material for star formation, outward and away from the galaxy's center. A galaxy that was actively forming thousands of new stars per year can see that rate drop sharply over cosmically brief timescales as its cold gas supply is heated, disrupted, and expelled. This is black hole feedback. Scientists confirmed it operates in nearby galaxies through observations of hot gas outflows, suppressed star formation in massive elliptical galaxies, and the tight mathematical relationship between a galaxy's total stellar mass and the mass of its central black hole. That relationship, holding across galaxies of vastly different sizes and environments, is one of the strongest pieces of evidence that the black hole and its host galaxy grow together, regulating each other through feedback. In the little red dots, this feedback was running at peak intensity. The black holes were feeding at extreme rates. The radiation and wind outputs were proportionately extreme, and the host galaxies were compact, meaning there was less distance between the central engine and the surrounding star-forming gas. Imagine a furnace inside a small room, rather than a large building. The heat fills the space faster and more completely. The disruption is total rather than partial. Some research teams studying little red dot candidates with Webb found evidence of broad emission lines in their spectra, which is a signature of gas moving very fast in the vicinity of an active black hole. Velocities in these outflows reached thousands of miles per second. Gas moving that fast can escape the gravitational pull of a compact early galaxy entirely, carrying with it the fuel that would have formed future generations of stars. The black hole was effectively eating its own galaxy's future. What remains after this process completes is a galaxy stripped of its cold gas, dominated by old stars, slowly aging and dying, centered on a massive but now dormant black hole with nothing left to consume. A quenched system. Quiet, massive, red. The efficiency of this process in the early universe explains something that had puzzled astronomers for years before Webb. Why the most massive galaxies in the modern universe tend to be the oldest and the least active. They burned brightest, earliest, and most violently. Then they went silent. The violence that built them was the same violence that ended them, and the scale of what that violence produced across the entire early universe was something that the next measurement would make almost impossible to process. Every telescope ever built by humanity is a compromise between what you want to see and what the physics of light, mirror size, and detector sensitivity actually allows you to capture. Hubble was a masterpiece of engineering for its era. but its vision was shaped by the wavelengths of light its designers prioritized and the mirror size they could practically launch into orbit. James Webb represents a different set of choices, made specifically for the problem of seeing the early universe. Understanding those choices explains why Webb could find the little red dots when every previous instrument missed them. The primary mirror on Webb spans almost 21 feet across, roughly 3 times the diameter of Hubble's main mirror. Size matters in telescope design because a larger mirror collects more light. More collected light means faint, distant objects become detectable that would otherwise remain invisible. Webb's mirror is so large that it had to be built in segments, 18 hexagonal panels coated in gold that folded up for launch and deployed in space. Gold coating is significant. Gold reflects infrared light with exceptional efficiency. Infrared is the wavelength range Webb was built to prioritize, and gold-coated mirrors lose far less of that precious, faint infrared signal than mirrors optimized for visible light. Why infrared specifically? Because of redshift. Light from objects in the very early universe has been traveling for over 13 billion years through an expanding cosmos. As space expands, it stretches the wavelength of the light traveling through it. Light that began its journey as visible or ultraviolet radiation arrives at Earth, stretched into the infrared range. The farther the source, the more extreme the stretching. An object at a distance corresponding to the first billion years of the universe emits what we would recognize as visible light at its source. By the time that light reaches Webb, it has been stretched to wavelengths roughly 10 to 15 times longer, deep into the infrared spectrum. Hubble, with limited infrared sensitivity, could catch only a faint trace of this signal. Webb catches the full picture. Webb also operates at an extremely cold temperature, around -447 degrees Fahrenheit. This is essential because warm objects emit infrared radiation, and a warm telescope would flood its own detectors with self-generated noise. Webb keeps itself cold by deploying a 5-layer sun shield the size of a tennis court, blocking heat from the sun, Earth, and Moon simultaneously, and allowing the telescope to radiate its own heat away into the cold of deep space. The cold detectors, the large gold mirror, the infrared sensitivity, the deep space location far from Earth's atmospheric interference. All of these elements combine to give Webb a capability that no ground-based or previous space-based telescope could match for observing the distant universe. One simple comparison captures the scale of the improvement. Hubble's deepest field image, built from weeks of exposure, showed galaxies out to roughly 13 billion light-years with limited detail. Webb imaged a comparable region in a fraction of the time, with resolution sharp enough to measure individual galaxy structures at the same distances. That capability is why the little red dots went from archived anomalies to a crisis for cosmological models in the span of 2 years. Webb did not just see farther, it saw a fundamentally different universe than the one previous tools had access to. And the deeper it looked, the more that universe diverged from expectation. Something even stranger was waiting at the far edge of what the instruments could resolve. Light carries information, encoded in its wavelength, its intensity, and its precise color distribution is a complete record of where it came from, what produced it, and how long it has been traveling. Astronomers learned to read that record over the course of the 20th century, and the technique they built, spectroscopy, became the most powerful tool in observational astronomy. Point a spectrograph at a distant object, split its light into its component wavelengths, and you get a fingerprint that reveals the object's chemical composition, temperature, density, and motion. The motion part is where redshift comes in. When a light source moves away from an observer, the waves of light it emits get stretched. Each wave crest has a slightly longer distance to travel than the last, so the wavelength increases. Longer wavelengths in visible light correspond to the red end of the spectrum, which is why the effect is called redshift. When a source moves toward you, the opposite happens and wavelengths compress toward blue. Edwin Hubble discovered in the 1920s that virtually every galaxy beyond our immediate neighborhood shows redshift, and the farther away a galaxy is, the more redshifted its light appears. This was the first observational evidence that the universe is expanding. Galaxies are not flying through space away from us. Space itself is expanding between them and us, stretching the light in transit. The redshift value, expressed as a number astronomers call Z, measures how much a galaxy's light has been stretched. A redshift of 1 means the light's wavelength has doubled. A redshift of 5 means it has been stretched to 6 times its original length. The little red dots that Webb detected sit at redshifts between 4 and 9, with some candidates potentially higher. At a redshift of 9, the light arriving at Webb's detectors left its source when the universe was roughly 500 million years old. That light began its journey in the ultraviolet range and has been stretched into the near-infrared by the time it reaches us. To see these objects at all, you need an instrument optimized for exactly those infrared wavelengths. The redshift also tells scientists the object's distance, but with a twist. The distance light has traveled is different from the current distance to the object, because space has been expanding during the journey. An object whose light took 13 billion years to arrive is currently over 46 billion light-years away, because the space between us and it has expanded continuously while the light was in transit. For the little red dots, measuring an accurate redshift was the critical first step in understanding what they are. A precise redshift confirmed their epoch, placed them in the correct phase of cosmic history, and allowed scientists to calculate their intrinsic luminosity by correcting for the distance. Those corrected luminosities were what caused the initial shock. Objects that appeared faint in Webb's images because they were extraordinarily far away turned out to be intrinsically among the brightest things ever detected from that era, once the distance correction was applied. A single photon, after traveling for over 13 billion years, still carried enough information to reveal a universe that should not have been possible. And the objects hiding behind those photons were about to become even harder to explain. The little red dots were the headline. But Webb was shattering records on multiple fronts simultaneously, and some of those side discoveries made the red dot problem look almost modest by comparison. Within months of beginning science operations, Webb confirmed the most distant galaxy ever spectroscopically verified at the time of confirmation. The galaxy, a compact collection of young stars existing when the universe was approximately 320 million years old, had its redshift measured with enough precision to establish its distance beyond any reasonable doubt. Its light left when the universe was roughly 2% of its current age. That record was broken again, and then again. By mid-2023, multiple teams had confirmed galaxies at redshifts pushing toward the edge of what Webb could detect, some of them existing in a cosmic era that, before Webb launched, was considered essentially inaccessible to direct observation. Each new distance record came with the same uncomfortable companion. The galaxy in question showed signs of being more developed, more structured, or more massive than standard models predicted for that epoch. The record breakers were not formless gas clouds catching their first light. Several of them showed spectral signatures indicating established stellar populations, meaning they had been forming stars long enough to have multiple generations of stars. One detection drew particular attention from the broader scientific community. Webb found a galaxy at extreme distance, showing a rotation curve, a measurement of how gas in the galaxy moves, indicating organized disk rotation. Disk galaxies, the kind with flat spinning structures like the Milky Way, are supposed to take billions of years to organize themselves from the chaotic early merging phase into a stable rotating disk. Seeing one at that distance, that early, with organized rotation, was described by one team member as finding a finished house on a construction site, where the foundation should still be wet. Webb also detected, in its first year, a galaxy that appeared to contain a population of stars significantly older than the galaxy's supposed age. When your measurements say the stars inside a galaxy formed before the galaxy itself existed, it forces a rethinking of either the stellar age estimate, the distance measurement, or the models predicting how early organized galaxies can form. In most cases, careful reanalysis refined the measurements and reduced the tension without eliminating it entirely. Science rarely overturns itself cleanly. The process is iterative, with each new analysis narrowing the uncertainty rather than producing a single definitive verdict. But across all these individual detections, a pattern held. Webb was consistently finding objects earlier, more massive, and more structurally developed than models predicted they should be. The errors and uncertainties shifted individual data points, but did not erase the overall direction. The universe had been more productive earlier than humanity's best models gave it credit for. And sitting behind all of these extraordinary objects, providing the gravitational infrastructure on which everything assembled, was something that had never been directly seen, only inferred, since its existence was first proposed decades earlier. What dark matter was doing in the early universe, and whether it behaved the way models assumed, was about to become a much more urgent question. Among Webb's most immediately alarming discoveries were not the little red dots themselves, but objects sitting nearby in the same deep field images. Fully structured, recognizable galaxies at distances that should have made their existence impossible. Call them the impossible galaxies. Researchers gave them more technical designations, but the informal name spread quickly through the community, because it captured exactly what scientists felt when the data arrived. These galaxies showed spiral structure, clear, organized arms curving outward from a central core, the same morphology as the Milky Way and its nearest neighbors. Spiral structure requires a galaxy to have settled into a stable rotating disk, a process that depends on repeated merging events, smoothing out over time. Internal gas dynamics stabilizing, and angular momentum distributing evenly across the disk. The timescales typically cited for a galaxy to develop recognizable spiral structure range into the billions of years. The impossible galaxy showed it within the universe's first billion years. The immediate response from some researchers was to question the distance measurements. A spectroscopic redshift is extremely reliable, but in a handful of early cases, initial distance estimates based on photometry, meaning color-based guesses rather than direct spectral measurement, had turned out to be overestimates. If a galaxy thought to be at extreme distance was actually closer, the structural timeline problem would dissolve. Webb's follow-up spectroscopic observations confirmed the distances in the most studied cases. The galaxies were where the initial data said they were. A second line of defense involved the models themselves. The simulations used to predict early galaxy morphology carried significant uncertainties in their input parameters, and some researchers argued that tuning those parameters within acceptable ranges could produce occasional early spirals without breaking the standard framework. This argument worked for one or two objects. It strained credibility when applied to a growing catalogue of such objects, detected across multiple independent surveys. A third interpretation, more disruptive, suggested that the processes by which angular momentum builds up and organizes a galaxy into a disk may operate faster under early universe conditions than the models assumed. Denser gas, stronger gravitational gradients, and the absence of the metal-rich feedback processes that complicate modern galaxy formation might allow a disk structure to emerge in a fraction of the time it takes today. This idea has attracted serious theoretical work and remains an active area. If early disk formation happens faster than standard models predict, then the impossible galaxies are possible. The models need adjustment. and the adjustment has cascading implications for every subsequent phase of cosmic evolution. What made this discovery connect so directly to the little red dots was the shared implication. Both the red dots and the impossible galaxies pointed toward an early universe that assembled structure with an efficiency and speed that the standard model systematically underproduced in its simulations. The two anomalies were probably not unrelated. A universe that builds black holes faster than predicted is likely also a universe that builds galaxies faster than predicted. They share the same environment, the same gas supply, and the same gravitational dynamics. The same root cause, whatever it was, probably drove both phenomena. Finding that root cause was where the most intense theoretical work was being directed, and one candidate for that root cause was something that had been hiding in plain sight in the cosmological framework for decades. Dark matter does not emit light. It does not absorb light. It interacts with normal matter only through gravity. You cannot see it, taste it, touch it, or detect it with any instrument designed to catch electromagnetic radiation. And yet without it, the universe as we know it could not exist. The evidence for dark matter is overwhelming and comes from multiple independent directions. Galaxy rotation curves show stars in the outer arms of spiral galaxies moving faster than they should, if only the visible mass were present. Something extra is providing gravitational pull. Gravitational lensing, where massive objects bend light passing nearby, consistently reveals more mass in galaxy clusters than the visible matter can account for. The cosmic microwave background, the oldest light in the universe, carries imprints of early density fluctuations that only make sense if a large component of non-interacting mass was present from the beginning. The standard cosmological model includes dark matter as its dominant form of matter, roughly 5 times more abundant than the ordinary atoms that make up stars, planets, and people. Under this model, dark matter formed gravitational wells first, and ordinary matter fell into those wells, eventually producing the galaxies and structures we observe. The dark matter web, a vast filamentary network of invisible mass threading the universe, is the skeleton on which all visible structure hangs. In the early universe, the behavior of dark matter was critical. The speed at which dark matter clumped together determined how quickly the first gravitational wells formed, which determined how quickly the first gas clouds could collapse, which determined how early the first stars and galaxies ignited. Standard model dark matter, called cold dark matter, consists of slow-moving particles that clump efficiently on large scales. The model predicts specific rates of clumping at specific epochs. Webb's findings, with their too massive, too early structures, suggest those rates may have been faster than the cold dark matter model produces. This has opened serious discussion about alternatives. Warm dark matter, made of faster-moving particles, would produce somewhat different clumping patterns. Self-interacting dark matter, which collides with itself in ways standard dark matter does not, could produce denser early concentrations. Fuzzy dark matter, an exotic quantum variant, would suppress small-scale structure formation, but allow different large-scale behavior. None of these alternatives fits all observations perfectly. Cold dark matter remains the best overall match to the full body of evidence, but the specific tension around early structure formation has given alternative dark matter models new relevance and new urgency. If dark matter clumped faster in the early universe than current models predict, perhaps due to a property we have not measured, then early galaxies had deeper gravitational wells to fall into, assembled faster, and produced the extreme objects Webb found more readily than simulations suggest. Dark matter would be the unseen accelerant behind everything Webb discovered, and there was one more piece of evidence suggesting the early universe operated with a kind of energy and organization that our current models only partially capture. It was hiding in the frequencies of light these objects emitted. and it pointed toward a question that no instrument in human history had been designed to answer. Every object in the universe broadcasts. Stars pour out electromagnetic radiation across a wide range of frequencies. Black holes and their surrounding disks emit radio waves, X-rays, infrared, and visible light simultaneously. Gas clouds absorb and re-emit at specific frequencies tied to their chemical composition. The universe is saturated with signals, most of them produced by purely physical processes, carrying no message beyond the laws of thermodynamics and atomic physics. For a brief period in the 20th century, before the scale of the universe's natural radio emissions was fully mapped, some scientists entertained the possibility that certain radio signals from deep space might carry something more. The search for extraterrestrial intelligence built its early programs around scanning radio frequencies, where artificial signals might stand out against the natural background. The frequencies most scrutinized were hydrogen emission lines, specific radio wavelengths produced by hydrogen atoms that blanket the universe and were considered a likely communication channel for any technologically advanced civilization. The logic was simple. Hydrogen is the most abundant element in the universe, and any intelligence sophisticated enough to build radio transmitters would likely know this. The little red dots are not alien signals. That needs to be stated directly. They are natural astrophysical objects, and the radiation they emit follows patterns fully consistent with physical processes. Active black holes, superheated gas, and extreme stellar populations produce exactly the kinds of broad, energetic spectra Webb detected. But the coincidence worth noting is this: the frequencies at which some little red dot's radiation arrives at Earth after being redshifted during its 13 billion year journey occasionally overlap with the frequency ranges that early radio telescope surveys searched for artificial signals. Objects that were not even known to exist when those searches were designed were producing natural backgrounds in the same frequency windows. This matters practically. Future deep space communication searches need to account for the full population of natural emitters, including objects like the little red dots, to accurately distinguish genuine anomalies from astrophysical backgrounds. Webb's catalogue of early, energetic objects has directly improved the accuracy of that background model. It also matters philosophically, in a quieter way. The universe contains natural processes so energetic and so compact that they can, entirely without intention, produce electromagnetic outputs rivaling what an advanced civilization might generate. The sheer scale of what physics does without direction is a useful frame for understanding the challenge of detecting anything artificial against it. The fact that we can now map natural sources at those distances with Webb-level precision is a genuine scientific advance in the search problem, regardless of whether any signal is ever found. And it raises a question that the little red dots made newly concrete. If the early universe was this energetic, this structured, and this productive, what does that mean for the probability that the conditions producing complex chemistry and eventually life arose somewhere in those 13 billion years of cosmic history before Earth even formed? That question had no immediate answer, but it now had much better data to frame it with. Comparisons are the only tool that makes cosmic scales feel real. The Milky Way is a large spiral galaxy. It spans roughly 100,000 light-years from edge to edge. Traveling at the speed of light, crossing it would take 100,000 years. It contains somewhere between 200 billion and 400 billion stars. Its central black hole, Sagittarius A star, holds a mass of about 4 million times our Sun. The galaxy has been building for over 13 billion years and represents one of the largest structures in our immediate cosmic neighborhood. By every human standard, the Milky Way is incomprehensibly large. Now place a little red dot next to it. The little red dot's host galaxy, in many observed cases, appears significantly smaller than the Milky Way, some estimates placing the host structure at only a few thousand light-years across rather than 100,000. Smaller, more compact, far less spatially extended, but the black hole at its center carries a mass potentially exceeding 1 billion times our Sun. That is 250 times the mass of Sagittarius A star, packed into a galaxy smaller than ours. Existing when the universe was less than 1 billion years old, the energy output from that central black hole during its active feeding phase exceeds the combined light of every star in the Milky Way by factors ranging from hundreds to thousands. So you have a smaller galaxy hosting a vastly more massive and more active black hole, pouring out more energy per unit of time than our entire galactic home has ever produced at any point in its history. The violence at the center of a little red dot, translated to human scales, would look something like this. Imagine the Sun replaced not by a slightly larger or brighter star, but by a source of radiation so intense that it would sterilize every planetary system in the Milky Way simultaneously. The jet emanating from the black hole would extend beyond the galaxy's edge and pour energy into surrounding space at a rate that heats entire gas clouds millions of light-years away. That is what was happening routinely across hundreds of these objects in the young universe. The modern Milky Way is, by comparison, a calm and stable environment. Sagittarius A star occasionally consumes small gas clouds and produces brief increases in X-ray output, but its feeding rate today is tiny relative to its theoretical maximum. Our galaxy has been in a relatively quiet phase for billions of years. This contrast between the early universe's violence and the modern universe's relative calm reflects a real shift in cosmic conditions. The early universe was dense, gas-rich, and filled with objects feeding at full intensity. As the gas was consumed, expelled, or locked into stars and planets, the available fuel for extreme activity decreased. The universe cooled down, structurally and energetically. The peaceful solar system you exist inside is, in a very real sense, a product of that cooling. A stable star orbiting within a stable galaxy in a universe that burned through its most violent phase billions of years before Earth formed. How close the balance actually was, how different things might have been, was a question the little red dot data made uncomfortably vivid. When the first confirmed little red dots were identified in early Webb data, the count was small enough to memorize. A handful of objects, intriguing, anomalous, but possibly edge cases. Unusual objects always appear in large surveys. Astronomy has a long history of one-off detections that turned out to be instrumental artifacts or rare astrophysical flukes with no broader significance. The little red dots refused to stay rare. By the end of Webb's first full year of science operations, catalogued candidates numbered in the dozens. By mid-2023, multiple teams had independently assembled lists running into the hundreds. Each new deep field observation added more. Each reanalysis of existing data with refined selection criteria found additional candidates that initial passes had filtered out. The objects were common, across different patches of sky, at consistent distances, corresponding to the first billion years of cosmic history. Little red dots appeared repeatedly and predictably. They were a population, a distinct class of object, occupying a specific niche in the early universe, producing a specific range of luminosities and colors that Webb's instruments could identify reliably. This shift from anomaly to population was scientifically significant in a way that individual detections cannot be. A single unusual object leaves open the possibility of misidentification. A population of hundreds, distributed across independent observations by multiple research groups, implies a real and recurring physical phenomenon. It also meant the contribution of these objects to the early universe's total energy budget and mass budget was substantial. If hundreds of little red dots exist within the region Webb can survey, and Webb surveys only tiny fractions of the total sky, the extrapolated total population across the full early universe runs into potentially millions of such objects. Millions of sources, each outshining entire galaxies, each hosting black holes of hundreds of millions of solar masses, each pumping radiation and outflows into the surrounding universe during the first billion years of cosmic history. The energy they collectively injected into the early universe was enormous. Their contribution to reionization, the process by which the early cosmic fog cleared, may have been larger than previously attributed to any single class of object. Their combined black hole masses, if representative of the broader early universe population, implied a total reservoir of supermassive black hole mass in the young cosmos, far exceeding what pre-Webb estimates had suggested. Every model that touched on early black hole formation, early galaxy assembly, the reionization history, or the growth of cosmic structure needed updating. The inputs had changed, and the models being updated were already strained by the earlier discoveries. Adding a large population of extreme early objects into the calculations amplified every tension that had emerged since Webb's first science images arrived. Astronomers found themselves in the unusual position of having more high-quality data than their theoretical framework could comfortably absorb. The data was not ambiguous. The framework was the problem. Something big was going to have to give, and the next generation of instruments was already being designed specifically to push into the territory where the answers might be hiding. James Webb is extraordinary. It has redefined the observational frontier and produced more cosmological surprises per year of operation than any telescope in history. But it has limits, and those limits matter enormously for understanding the little red dots and the questions they raise. Webb's primary limit is time. Long exposures are required to detect the faintest, most distant objects, and the telescope's schedule is competitive. Thousands of proposals arrive from research teams around the world requesting observation time. Each approved program gets a slice of a calendar that fills up years in advance. The deep field images that revealed the little red dot population in detail required dozens of hours of continuous exposure for relatively small patches of sky. Surveying a large fraction of the observable sky at the depth needed to catch objects from the early universe is beyond what Webb can accomplish in its operational lifetime. The second limit is angular resolution. Webb's mirror is large, but resolving the internal structure of objects over 13 billion light-years away pushes even its capabilities. Many little red dot host galaxies appear essentially point-like in Webb's images, meaning the distinction between the central black hole's emission and any surrounding stellar population cannot be cleanly separated. Understanding whether these objects are black hole-dominated or starburst-dominated, the central unresolved question, requires resolving structure that sits below Webb's resolution threshold for many targets. The third limit is wavelength range. Webb covers infrared beautifully, but does not observe at X-ray or radio wavelengths. X-ray observations are critical for confirming black hole activity directly, since the innermost regions of an accretion disk emit strongly in X-rays. Radio observations can detect jets and large-scale outflows. Some little red dots have been followed up by X-ray space telescopes, but those telescopes have less sensitivity at the relevant distances than ideal. These gaps have pointed directly to the next generation of instruments currently under development. The Nancy Grace Roman Space Telescope, planned to launch in the late 2020s, will survey an area of sky roughly 100 times larger than Webb can cover in the same exposure time. Its wide-field imaging capability will find enormous numbers of early universe objects that Webb's narrow field would miss, building statistical samples large enough to test models with genuine confidence. On the ground, The extremely large telescope under construction in Chile will use a primary mirror nearly 130 feet across. Its resolution for nearby and moderately distant objects will be extraordinary. Combined with adaptive optic systems that correct for atmospheric blurring, it will resolve structures in distant galaxies that even Webb cannot separate. For X-ray coverage, a next-generation X-ray observatory with significantly greater sensitivity than current instruments would transform the ability to directly confirm black hole activity in little red dot candidates. And proposed future radio arrays would map the early universe's gas distribution with a precision that would trace the filaments feeding the first extreme objects in unprecedented detail. Webb opened the door. The instruments being built now are designed to walk through it. What they find in the coming decade will likely determine whether the standard model survives in recognizable form or requires the most fundamental revision in the history of modern cosmology. The most important observation in human history might be only a few years away. Science has rewritten its own foundations before. Newton's laws of motion and gravity stood for over 2 centuries as the most precisely verified framework in the history of human knowledge. Then Einstein's general relativity arrived and revealed that Newton's framework was an approximation accurate enough for everyday scales, but wrong at the extremes of speed and gravity. The solar system's planets still move according to Newton's equations, with excellent precision. But the orbit of Mercury, the bending of light around the sun, and the existence of black holes all required a deeper theory to explain. General relativity did not erase Newton, it subsumed him, extending the framework into territory where the simpler version failed. The current standard model of cosmology may be standing at a similar moment. The core of that model, the Big Bang, expansion, dark matter, dark energy, is almost certainly correct in outline. The evidence for each of these components is too strong and too diverse to be overthrown by any single telescope's findings. But the specific details of how structure assembled, how fast early black holes grew, how efficiently the first galaxies formed stars, these are the edges of the framework where the approximations may be breaking down. Just as Newton worked perfectly until you moved fast enough or got close enough to a massive object, the standard model works well for the modern universe, but may need a deeper version to describe the early universe correctly. What that deeper version looks like is genuinely unknown. The candidates range from modest parameter adjustments to radical reconceptions. Some physicists are exploring whether the initial conditions set by inflation were different from the standard assumption, in ways that seeded denser early structures. Others are investigating whether dark matter has properties, self-interaction, quantum behavior, or variable mass that produce faster early clumping. A few are questioning whether the value of dark energy has changed over cosmic time in ways that altered the expansion history. Each of these modifications produces different predictions that future telescopes can test. The process of elimination is already underway, but there is also the possibility, less discussed in polite scientific circles but raised seriously by a small number of physicists, that something more fundamental is wrong, that the initial conditions of our universe are simply unusual within some larger ensemble of possible universes, and that a universe producing the early structure Webb found is the expected outcome of those unusual conditions, rather than a failure of the model. This anthropic reasoning, the idea that observers like us can only exist in universes that happen to produce the conditions allowing our existence, makes specific predictions extremely difficult. It is scientifically uncomfortable, precisely because it is hard to test. What is clear is that the universe Webb is revealing operates by rules that the rules we wrote down do not fully capture. The rules are not wrong, they are incomplete. And finding what is missing will require thinking at a scale that matches the objects that exposed the gap. Objects that outshine galaxies, objects born enormous, objects from a universe that did not wait for permission to build what it built. It is tempting to treat all of this as abstract, distant objects, ancient light, equations under revision, something happening far away and long ago with no connection to the ground under your feet. The connection exists. It runs through chemistry. Every atom heavier than hydrogen and helium was forged inside a star. The carbon in your DNA, the oxygen filling your lungs. None of these elements existed at the moment of the Big Bang. They were built inside stars over billions of years and scattered into space when those stars died. The little red dots and the violent early universe they represent were part of the chain of events that made this chemistry possible. The first generation of stars, born inside the early galaxies in extreme environments Webb is now observing, produced the first heavy elements. They exploded, seeded their surroundings, and enabled a second generation of stars with more chemical complexity. And so on, across billions of years and countless stellar generations, until eventually a cloud of enriched gas in an outer arm of the Milky Way collapsed into a star with a disk of planets, one of which developed liquid water, chemistry, and life. The violence of the early universe was not separate from the existence of life on Earth. It was a prerequisite. The little red dots and their extreme black holes drove energy into the surrounding universe, heated and enriched gas clouds, and contributed to the cascade of chemical evolution that made complex molecules possible. A universe that did not have such intense early activity might have assembled more slowly, produced fewer heavy elements in the critical early window, and presented very different conditions for chemistry in its later epochs. There is also a forward-looking implication. The universe's current relatively quiet phase, with star formation rates much lower than the early cosmos, reflects the consumption of available fuel. Stars continue forming in gas-rich regions, but at a pace far below the early universe's peak. The era of violent galaxy building and extreme black hole activity has passed. Earth exists in the long, quiet afternoon following the universe's turbulent morning. The Sun is a middle-aged, stable star burning hydrogen at a measured rate, expected to continue for another 5 billion years. That stability, rare against the backdrop of the early universe's chaos, is what allows life to persist and evolve across geological timescales. Understanding the early universe, including the extreme objects Webb found, is understanding the full arc of cosmic history from which this stable moment emerged. Every discovery about the early universe adds a layer to the story of how a cosmos born in fire and violence became a place where, in at least one corner, organisms can sit and wonder about where they came from. The answer to that question keeps getting older, deeper, and stranger, and the deepest, strangest part had not yet been fully confronted. Every scientist who has spent serious time with the little red dot data comes to the same stopping point. The objects are real, the data is strong, the implications for cosmological models are significant and mounting. The theories about their origin, their feeding mechanisms, their eventual fate, are productive and testable. Science is making progress on all of these fronts, and then someone asks the one question that sits underneath all the others, and the room gets quiet. Where did the very first black hole seeds come from? Every model of black hole growth, including direct collapse, requires a starting point, a seed, a first object with enough mass to anchor further growth. Direct collapse produces seeds far larger than stellar mass black holes, but it still requires an initial gas cloud to collapse, and that cloud existed within a universe that had already been running for some time. Go back further, before the first stars, before the first gas clouds had collapsed, before there was any structure at all. The universe at that stage was a smooth, nearly uniform sea of matter, with tiny density variations, the imprints of quantum fluctuations from the inflation epoch, stretched to cosmic scales. From those quantum fluctuations, everything formed. Every galaxy, every star, Every black hole, every planet, every living thing. The entire structure of the observable universe grew from ripples smaller than an atomic nucleus, stretched across the sky during a fraction of a second at the beginning of time. The density variations seeded by inflation were distributed statistically. Most regions had modest overdensities that eventually formed ordinary galaxies. A small fraction had extreme overdensities that may have collapsed directly into black holes before any star ever formed. These hypothetical objects, called primordial black holes, would have been born not from a star's death or a gas cloud's collapse, but from the raw density of the early universe itself, during the first fractions of a second after the Big Bang. Primordial black holes have been theorized for decades. They remain unconfirmed. No observation has directly detected one, but if they existed, they would provide exactly the kind of early seed mass that the models of superrapid black hole growth require. A primordial black hole carrying even a modest mass, born in the universe's first moments, would have 13 billion years worth of opportunities to consume surrounding material and grow into exactly the kind of monster Webb found sitting inside the little red dots. The question cannot be answered with current data. Webb cannot observe the universe's first fraction of a second. No instrument ever built or currently probe that era. The physics governing the density fluctuations of those first moments is described by a combination of general relativity and quantum mechanics, two theories that have never been successfully unified into a single coherent framework. The origin of the first black hole seeds may be permanently hidden behind the limits of what any telescope can physically observe. Every researcher studying the little red dots knows this. The objects Webb found are spectacular evidence of what happened one step downstream from that origin. But the origin itself, the first seed, the first collapse, the mechanism that started the entire chain, remains genuinely and possibly fundamentally unknown. Some questions in science eventually yield to better instruments and better theories. Some reveal that the asking itself was shaped by a wrong assumption, and a new framework dissolves the puzzle rather than solving it. And some questions simply wait, patient and open, at the edge of what human knowledge can reach. Step back from every individual discovery in the story and look at the shape of it. A universe is born from an extraordinarily hot, dense state. In its first fraction of a second, quantum fluctuations are stretched to cosmic scales, seeding the density variations from which all structure will grow. The universe expands and cools for hundreds of millions of years. Then, the first stars ignite, blasting ultraviolet radiation into the surrounding fog, beginning the process of reionization. And somewhere in that process, possibly from direct collapse, possibly from mechanisms not yet fully understood, the first supermassive black holes assemble. They consume surrounding gas at extreme rates. They blast energy into the surrounding universe. They grow to billions of solar masses while the cosmos is still in its infancy. Alongside them, the first galaxies form. Compact, dense, furiously productive, converting available gas into stars at rates hundreds of times higher than modern galaxies, building stellar populations in a fraction of the time the standard model allocated for the process. All of this happens in under 1 billion years. The universe has barely begun by cosmic standards, and it is already producing objects whose energy output defies the standard model's predictions and whose mass challenges every growth timeline in the theoretical literature. Then, gradually, the fuel runs out. The extreme objects quench. The blazing early black holes go dormant. The frantic star formation slows. The universe spreads out, cools further, and shifts into the longer, quieter phase of its middle history. The architecture left behind by that violent early phase, the distribution of massive galaxies, the network of dark matter filaments, the seeds of every future cosmic structure, shapes everything that follows, including the spiral arm of a relatively ordinary galaxy, where, billions of years later, a small rocky planet develops an atmosphere, oceans, and eventually organisms sophisticated enough to build telescopes. Those organisms point one of their telescopes, the most capable ever constructed, at the oldest light they can reach. And what they find there is a universe that built itself faster, more violently, and more efficiently than they had imagined. The story this tells is not about human smallness. That interpretation is too easy and too passive. The story is about the audacity of observation, the willingness to build a machine that can catch photons traveling for over 13 billion years and extract from them a precise account of objects that no longer exist in any recognizable form. The little red dots were gone before Earth formed. Their light has been traveling since before the solar system's first grain of dust condensed. And we caught it. We understood enough of it to know that our understanding was incomplete. That incompleteness is the most honest and the most exciting place science can stand. Every confirmed fact revealed by Webb carries at its edge a question that no current theory answers cleanly. The universe built itself too fast for our models, and our models in the face of that fact are doing what good models do: straining, adjusting, and pointing towards something deeper. Astronomy is standing at the edge of its most productive decade in history. James Webb will continue operations, gathering more data on the little red dots and the surrounding population of early universe objects. Each additional year of observations builds statistical samples that let researchers test models with increasing precision. New deep field programs are scheduled. Follow-up spectroscopy on the most extreme candidates will refine mass estimates and feeding rate calculations. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will survey sky areas roughly 100 times wider than Webb, where Webb finds hundreds of little red dots in small patches. Roman will find hundreds of thousands across vast stretches of the sky, building a catalogue large enough to map the full distribution of extreme early objects and trace their relationship to the large-scale structure of the early universe. On the ground, the extremely large telescope, currently under construction on a mountaintop in Chile's Atacama Desert, will begin operations before the end of this decade. With a primary mirror spanning nearly 130 feet, it will resolve structures in distant galaxies at scales that even Webb cannot achieve, separating the central black hole's emission from its surrounding stellar population in little red dot candidates. The key measurement needed to settle the black hole versus starburst debate will become possible for many of these objects. Gravitational wave observatories are also advancing. The merger of two supermassive black holes produces gravitational waves, ripples in space-time, at frequencies far below what current ground-based detectors can measure. A space-based gravitational wave detector, planned for the following decade, would be sensitive to exactly these low-frequency signals. Detecting gravitational waves from supermassive black hole mergers in the early universe would provide a completely independent way to measure the mass and distribution of early black holes, bypassing all the uncertainties in electromagnetic observations. Each of these instruments attacks a different piece of the problem. Together, they represent a coordinated assault on the questions Webb raised. The theoretical side is keeping pace. New simulations incorporating variable dark matter properties, modified inflation parameters, and more detailed models of early black hole seeding are being developed and compared against the accumulating Webb data. When the Roman telescope delivers its catalogue of hundreds of thousands of early objects, the simulations will face their most rigorous test yet. Models that survive that test will look quite different from the ones that existed before Webb launched. What the next decade will almost certainly produce is clarity on which modifications to the standard model are necessary and which are ruled out. Whether direct collapse black holes are the primary seed mechanism, whether the abundance of early massive galaxies reflects a change in dark matter behavior or a change in star formation physics, whether the little red dots represent a distinct class or a continuum of objects spanning from ordinary early quasars to genuinely new astrophysical phenomena? The answers are coming. The instruments are being built and launched. The theorists are developing the frameworks to interpret what those instruments will find. The universe spent 13 billion years building up to this moment of being understood. And the final piece of the puzzle, the one that has never quite been within reach, was the strangest of all. At the end of every scientific revolution, the most important insight is never what was discovered. It is what the discovery reveals about the limits of the questions that came before. The little red dots revealed something specific about our limits. For decades, cosmology built its models of the early universe without being able to see the early universe. The distribution of galaxies today, the properties of the cosmic microwave background, the measured expansion rate, were projected backward through equations to produce predictions about the past. The models were consistent with everything observable. They felt complete. They were not wrong. They were blind in one direction, and they filled that blindness with reasonable extrapolations that turned out to underestimate what actually happened. That is the cleanest description of where science stood before Webb, and it contains the most important open question that remains after everything Webb has found. The question is not whether the standard model needs revision. That is already settled. It does. The question is whether the revision needed is a refinement of the existing framework or a replacement of something more fundamental. Every previous revolution in physics fell into one of two categories. Newton, giving way to Einstein, was a deepening, a more complete theory subsuming a simpler one. But occasionally, science encounters a moment where the conceptual framework itself must change, where the vocabulary of the old theory cannot describe the new phenomena even approximately, and an entirely new language must be invented. The question that sits beneath the little red dots, at the level of primordial black hole seeds, of quantum fluctuations producing macroscopic structure, of an inflation epoch whose details remain unknown, is whether the early universe is describable by any combination of general relativity and quantum field theory in their current forms, or whether the conditions of those first moments require a theory of quantum gravity that does not yet exist. Loop quantum cosmology, string theory-derived cosmologies, causal set theory, and several other frameworks have proposed answers to what happens when quantum mechanics and gravity must operate simultaneously at the same scale. None of these frameworks has produced a confirmed prediction that distinguishes it from alternatives. The little red dots, by tracing the consequences of whatever happened in the universe's first moments, all the way to the first billion years of observable history, have given theorists new constraints. The objects that existed when the universe was young carry information about the seeds that produced them, and those seeds carry information about the physics of the very beginning. Reading that information backward, from the little red dots, through the first stars, through cosmic dawn, through reionization, through the dark ages, all the way to the initial conditions, is the scientific project that the next generation will inherit from Webb. The answer to what the early universe actually was, at the level of quantum gravity and the true nature of inflation, would not just close the little red dot chapter. It would answer questions that have been open since the moment physics first tried to describe the beginning of everything. 13 billion years ago, something happened so extreme and so fast that the universe it produced keeps surprising the descendants of the creatures it eventually generated. Those creatures built a telescope. That telescope found the surprise. And the surprise, followed far enough, leads somewhere that no instrument has ever gone. The universe is still pointing